Hi everyone and welcome. Thank you for joining us today as we launch the Far-Field ASR Leaderboard, a community benchmark co-developed by Treble and Hugging Face to help evaluate the performance of speech recognition systems in real-world conditions, where we have complex acoustics, noise, dynamics, and competing speech. Today, we're joined by industry leaders and researchers across the speech AI ecosystem to discuss the state of the art in ASR, to discuss the importance of high-quality benchmarking and different approaches to the Far-Field challenge. We have Dr. Eric Besem, audio ML engineer at Hugging Face, who will introduce the leaderboard and the motivation behind it. We have Dr. George Saon, manager of speech technologies at IBM Research and leader of the Granite speech effort. We have Nithin Koluguri, senior research scientist at Nvidia, whose work include the Parakeet family of ASR models. We have Julian Mack, member of technical staff at Cohere, working on speech and foundation models such as Cohere Transcribe. We have Dr. Shinji Watanabe, associate professor at Carnegie Mellon University and one of the leading researchers in speech and audio processing. And from Treble, Dr. Danny Nielsen, who will share details around the underlying evaluation framework behind the leaderboard. We're grateful to all the speakers for contributing their perspectives and looking forward to what should be a really interesting discussion. And with that, I'll hand it over to Eric to kick things off.
Thank you, Finna. This is Daniel from Treble here in Paris, and with me in Hugging Face HQ is Eric and my new buddy, Richie.
Hi, everyone. Thanks for having me. Say hi to the audience, Richie.
Hi, Daniel, Eric, and hello to everyone watching. Great to be part of the presentation.
So yeah, let's jump in about the leaderboard. First of all, I would like to thank all the guest speakers that we have for the webinar from Nvidia, Cohere, CMU, and IBM. Super awesome that they could join and share their experience in building ASR systems. So first of all, I want to just make a distinction between near field and far field. So near field is a type of evaluation that most of us are familiar with and something we cover extensively in the Open ASR Leaderboard. So that would be, for example, when you're talking into a phone or a headset or in your laptop. And applications for that would be, for example, voice notes, online meetings, call centers, podcasts. So we have amazing data sets and lots of benchmarks that really address this type of evaluation. Far field, on the other hand, I guess we can have a sort of rule of thumb. It's typically the situation where we're 1 meter or more away from a microphone or from an ASR system. And applications which people may be familiar with are smart speakers, smart appliances, conference room meetings where multiple people will be gathered around the table, or car assistants. And two challenges that come up within far field, quite notably, are reverberation because of this distance factor, and the other is a lower signal to noise ratio. So we have noisier audio that's now being fed into these ASR systems. Because the further away we are from the microphone, the more opportunity there are for other noise sources to also interfere with this target speaker or with this person that the system is trying to transcribe. And really in the last decade or so, we've seen a huge, let's say, boost, huge boom in far field contexts. So really this started off in 2014 when Amazon released Alexa, and soon after Google and Apple released their smart speaker devices. So really already in the last decade, we've seen a lot of use cases for far field in the smart speaker context, but also smart appliances and automotive as these models were integrated into different devices. In the past couple of years, we've seen some new types of devices arise. For example, the glasses in this collaboration between Ray-Ban and Meta, where primarily it's near field with the speaker there, but you would also have some far field contexts that would pop up, for example, in translation or speaking to other people when wearing those glasses. And another really hot topic that we see is humanoid robots. So in this situation, we'll see lots of far field types of problems and challenges that will arise. So already now, and also in the next few years, we're going to see these emerging interfaces with new challenges, with movement, not only from the speaker, but also from the devices, being outdoors, new types of acoustic conditions that our evaluations need to keep up with. And the way that people have tried to address far field currently, there's two main approaches, I would say. One of them is through data augmentation during the training of a model, and the other would be denoising. So for example, when it comes to data augmentation, you would have perhaps a data set of near-field audio, which we could call the target speech, and that will be augmented through acoustic propagation, but also through adding noise at different levels of SNR. And this acoustic propagation could be modeled by convolving a clean speech, so near-field audio with a room impulse response. So it's something that could be simulated through room acoustics. And then that would create a reverberant speech. And we could do the same thing for the noise, and then add together all those noise sources to get our far-field noisy audio. So that would be one way that models would try to incorporate some far-field robustness into their training so that they could be robust to a far-field ASR. The other popular approach is through denoising. So for example, you would take a fixed ASR system and you would pre-process it with some sort of front end or some sort of denoising algorithm. And this ASR could either be frozen and then we're trying to optimize this front end for our particular context. But we could also have different configurations where we try to train this ASR system with a given front end, or maybe we try to train both of them together. So that's another way that people could try to address this far field challenges. And quite naturally, the two could also be combined. And this would especially happen in the case where we introduce a microphone array. Because with multiple microphones, we could also do some spatial filtering to focus the ASR system in a specific direction to a specific user. So then we could train the denoiser, the ASR system alongside these data augmentation techniques. And so here I've just put a QR code to a blog that I co-wrote during my time at Sonos, because this is really one of the challenges we faced. We had several speakers that we had to design ASR systems for, and data augmentation was a huge part, but also accounting for the denoising within the training was super important. So feel free to check out this blog for some more info on that. So in summary, we have different approaches to far-field ASR. One of them could be this standalone ASR system, which has had some sort of augmentation in its training. And the other approach would really to explicitly add a denoising algorithm in front of the ASR system. And then the challenge that comes up when we want to do far-field evaluation is all the combination of conditions. It could be the combination of microphone arrays and devices with front ends, with ASR systems, but also the large number of conditions that different communities may be interested in. It could be the types of rooms, the distances, the level of SNR, the noise types. And then this type of data collection really does not scale well if we want to handle all of these situations. And this is where simulation can really play a huge part, and especially high quality simulation. And this is what we're trying to do with the FFASR Leaderboard, or FFASR for short. What we're trying to do here is we're bridging the high fidelity simulation from the Treble team, so their ability to handle complex room settings, complex acoustic conditions, but also what's really, really interesting is how they can handle movement of the device, but also the speaker, to just handle real world scenarios. And with that, we're bridging our expertise from Hugging Face with regards to evals with the OpenASR Leaderboard and all of our tooling with HF jobs and data sets and spaces. And this is just a perfect combination to bring to you the FFASR Leaderboard. To speak a bit about the data, so at the top of the leaderboard, you'll see these different data sets, which you can toggle on and off. So there is this near field speech data, which is something which would be more familiar to people, or it's more similar to what you would see in the OpenASR Leaderboard. So there, the Treble team has collected 8 hours of near field audio, so less than 1 meter to remind you, in an anechoic chamber. So this is a room with practically no reverberation. And the motivation behind this is to really get a clean audio without reverberation so that we can augment it with the expected reverberation of a particular room. And this data set is also going to be is a private data set, so we can avoid test set contamination from any of the models. So that's the base data set, which is very similar to what you would find on the OpenASR Leaderboard. And then on top of that, we're going to be doing these data augmentations, which I mentioned before. So with the Treble SDK, 14 fully furnished rooms have been simulated in different SNR conditions, high, mid, and low, and in different types of rooms. So more household type of situations like bathrooms, living rooms, and hallways, but also more, let's say, non-household settings such as meeting rooms, offices, and classrooms. And when we're adding noise, we're also adding noise that's been measured in an anechoic chamber to really reduce any type of reverberation that could be coming from other types of rooms. And so this data set is also going to be privately held. It's going to be a holdout set similar to near-field speech. But if you would like to see a data set that's similar to that, I encourage you to check out the Treble 10 data set, which is a release we collaborated with Treble late 2025. And you'll see similar types of room settings, but different room impulse responses, which you could use for your own evaluation or training purposes. On top of those data sets, we also have a data set that handles movement of the speaker, again, in high, mid, and low SNRs. And really the distribution of rooms and noise has been, we tried to keep it very similar to the non-moving SNR cases. So you can really see this difference of how movement affects performance. And then two other data sets, which are toggle off by default, are what we call the lab measured and lab simulated data sets. So lab measured is far-field measured data, unlike the other, which is simulated, which has been measured in the Treble offices under 3 acoustic conditions. And then the corresponding conditions have been simulated within Treble's SDK. And the goal of these two data sets are to really quantify this sim to real gap, because naturally we may have the question, okay, how do we know that this simulated acoustic conditions generalize to real world ones? So the purpose of these two data sets is really to see how actually close they are and how we can trust the simulation from the high, mid, and low SNR, and also their moving variants. So by default, those data sets are not incorporated into the average word error rate that you'll see on the leaderboard. On the analysis, so there's all sorts of metrics that you can observe. The main two metrics, similar to the OpenASR leaderboard, are average word error rate and RTFX. And on the analysis tab, you'll see a Pareto front, similar to on the OpenASR leaderboard, where the evals, we'll plot along these two axes. And just to mention, the evals for this are done on an Nvidia L4 GPU with a batch size of 1. And all of this is getting automated through HF jobs, so that we can ensure a consistent evaluation framework for all the models. On the submission process, there's a different tab to submit new models to be incorporated into leaderboard. So unlike the OpenASR leaderboard, where the submissions happen through GitHub, for the FFASR leaderboard, they'll happen through the submit tab, where you can specify a model ID on Hugging Face that you would like to be added to the leaderboard, any unique library requirements that it may need, and then you can also specify a custom evaluation script. So here's just a bigger view of that. And what's super interesting about this custom evaluation script is that this is where we can add different denoising algorithms. So what we were talking about before, decoupling the front end and the ASR system. So this is where the community can play around with different denoising algorithms. And this is where we're really excited to see contributions from people who may not necessarily be in the model training side, but on the denoising side of the community. So we're really excited for contributions on that side. And so just a reminder of all this far-field approaches. So these are all of the cases that we would love and we are striving to cover with the FFASR leaderboard. So these standalone ASR systems and these front-end plus ASR systems. Currently, what you'll see as we launch the leaderboard are primarily these models that have been trained with augmentation, as this far-field augmentation as one of the ways to improve robustness. But with this leaderboard, we're excited to see contributions now from people who maybe use these as base models, who retrain models to really tackle the whole spectrum of approaches for far-field ASR. So our goal with the FFASR leaderboard is really to enable this standardized far-field ASR evaluation for the community. So moving forward, the goal of the FFASR leaderboard is to be an evolving benchmark, much like the OpenASR leaderboard, that's shaped by you, by the community, by voice AI developers and users. And those could be contributions on the models, so more open source models, but also we're open to API models as in the OpenASR leaderboard, new acoustic conditions that you think could be of relevance, public data sets that you think are, especially far-field measured ones, that could be of relevance for the FFASR leaderboard, denoising algorithms. Now that we've enabled this opportunity to customize the evaluation scripts, we're excited to see contributions for denoising algorithms off of these baseline models. And of course, hardware, simulating different hardwares, because as we mentioned before, microphone arrays are a common way to incorporate spatial filtering for far-field robustness. And for example, on Reach, we got 4 microphones here, and it would be great to add different hardware that you think could be of relevance. And I know one friend of mine would be super excited to be on the leaderboard. Isn't that right, Richie?
I'd love to. Expanding to multi-microphone benchmarking with my recording sounds interesting. Let's do it.
Nice. So with that, thank you for joining, and let's move it on forward to the guest speakers.
Hi everybody, I'm George Saon. Welcome to IBM Yorktown Heights. I'm a manager of speech technology and in charge of Granite Speech, which is our LLM-based ASR. The outline of my talk is I'll mention a brief history of our modeling approaches and techniques for ASR at IBM from the 90s until now. And then I'll dive a little bit into Granite Speech, which is our current open source speech-aware large language models. And I'll show some results on the Hugging Face Open ASR Leaderboard and slowly transition to highlighting the importance of working on Far-Field ASR and noise-robust ASR. And I'll illustrate two research efforts that we had for noisy and far-field microphone speech, one which was with McDonald's for automated drive-through ordering, and one which was with Australia's Royal Flying Doctor Service. And I'll summarize with some thoughts on the benefits in our mind of the FFASR leaderboard for the speech community. At IBM, we went through several paradigm shifts for ASR. In the 90s until 2018 or so, we used hybrid HMM-based models where we changed the emission likelihood or observation model from Gaussian mixture models to deep neural nets and then convolutional neural nets. And then from 2018 or so, we transitioned to end-to-end approaches, first using recurrent neural network transducers with bidirectional LSTMs as an encoder. Then we switched to CTC with conformer acoustic encoders and n-gram language models compiled into WFSTs. And now we're looking at speech-aware large language models using conformer acoustic encoders. Our main work right now is called Granite Speech, which is our open source LLM-based speech recognition and speech translation models. And the characteristics are that we support multilingual ASR for 5 European languages and Japanese, and bidirectional English to foreign and foreign to English speech translation. And for ASR and translation, we support keyword list biased recognition, where a user can provide terms of interest that they want to get recognition right for. We support speaker labels and transcripts, which we term speaker attributed ASR. We can provide word-level timing information without using an external model. And through a change of prompt, we can opt for outputting punctuation and capitalization or not. Another characteristic is that our model is fully open weights with an Apache 2.0 license. It can be downloaded from Hugging Face with no restrictions. And in terms of architecture, this is shown on the right. We were inspired by the SLAM and Salmon speech-aligned LLM architectures, where we use a conformer acoustic encoder and temporal downsampler and projector that maps the acoustic embeddings to the embedding space of the large language model. We concatenate that with the prompt embeddings, and the LLM is trained to predict the transcript for ASR or the translation for AST. Another characteristic of our models is that we are fully transparent about architectural details, training and inference methodology, and our models are trained only on public training data that's available to everyone or on SDG derived from public data. And all the details about architectures and training and inference are on the model cards on Hugging Face or on papers that are linked from those model cards. In addition, we provide Python notebooks for fine-tuning our models for example, to a language that's not supported currently. And this is part of the small audio toolkit. And we also provide speculative decoding for accelerated inference with our models. In terms of our latest releases, we have 3 models on Hugging Face right now. Top left is our base model, which was optimized for accuracy and provides punctuation and capitalization, and the keyword list biased ASR. Our second model, termed Dash Plus, adds additional capabilities, which is SAA, speaker labels and transcripts, and word level timing information, and also has better accuracy on long-form ASR. And our third model uses a different architecture, which is non-autoregressive, and it's shown on the bottom right of the slide. And the idea is to take the CTC hypothesis from the encoder and provide parallel edits in one single forward pass, and this gives us an excellent throughput and accuracy trade-off. I'll show next some our performance on the Hugging Face Open ASR Leaderboard, which consists of 8 corpora that tests models on different genres and domains, like meeting transcriptions, earnings calls, YouTube videos, podcasts, read speech, and TED Talk transcription, and European parliamentary speeches. And as you can see, we started to participate in this leaderboard about a year ago, and our models reduced the error rate with each release. But what we wanted to highlight here is that we also focused on improving the functionality for our models. For example, by adding multilingual ASR, by adding Japanese and keyword biasing, and by adding punctuation and capitalization. And we also wanted to reduce the size of our models. Our initial models were based on an 8 billion parameter LLM. And now our latest models are based on a 1 billion parameter LLM and have an effective size of 2 billion parameters. And transitioning slowly into the subject of interest to the community, which is far-field robustness, we show on this slide our performance on AMI, which is meeting transcriptions, recorded meetings recorded in 2 different scenarios, one with a close-talking microphone and the other one with a single distant microphone. And we want to highlight the degradation in accuracy by, it's the same spoken material essentially, but because of the recording conditions, the degradation can be a factor of 2.5 to 4, depending on the model. This leads us to talk about 2 examples of noise-robust and far-field ASR that we participated in. One was a pilot experiment with McDonald's on automated drive-through ordering. And this project was super interesting because we faced several problems related to noise and crosstalk from neighboring ordering lanes, and from overlapping speech or side speech from non-primary speakers, such as children in the back of the car, for example. And we also had issues related to accents and code switching between Spanish and English when ordering. And the second engagement was done with Australia's Royal Flying Doctor Service, and there the setup was that the RFDS had small planes flying to remote places in Australia to provide health care. And they needed to take notes, doctors and nurses in those planes, they needed to take notes about for their patients. And they used our model in a very high noise because of engine noise from those small aircrafts. And I can play a clip. I hope it goes through. And as you can hear, it's those are extremely challenging conditions. And our models did quite well, even though they were not trained specifically for this task. But it does highlight the importance of noise-robust and far-field ASR. And this gets us to the last slide of the talk, which is we believe at IBM that it's very important to do realistic benchmarking of ASR systems. And we believe that the FFASR Leaderboard is very much a step in the right direction, because the existing benchmarks don't test models enough in difficult scenarios like high noise or reverb from different room configurations, or distant microphone speech, or conversational telephone speech, or overlapping speech, and so on. And another aspect is that back in the 90s and early 2000s, there used to be government funding for noise-robust ASR, such as the SPINE and also RATS, DARPA programs. But now this funding has dried up because ASR is considered to be a solved problem, incorrectly, we believe. And I hope that the community will coalesce around this effort, this FFASR leaderboard, because hopefully participants can generate realistic training and development data. And we also encourage the organizers of that leaderboard to cover multiple domains, genres, and accents. And maybe they can source clean data from public corpora, but apply their simulation to generate noisy and far-field data. And we would also hope that there will be a way to distinguish between ideas that advance the field and versus just training on more diverse data. And this concludes my talk. Thank you very much.
Hello everyone, thanks for having me. I'm Nithin. I'm here to talk about the Nemotron speech family of models and how they are built, especially for handling the robustness. And today I'm gonna go over who we are, what we do, what are the models we built, and how we build them, especially for handling the noises, and how our models are better in terms of like speed, and also how we train them, and why the Far-Field ASR leaderboard is really important. So first, who we are. So we are Nvidia Nemotron speech team. Our goal is to train state-of-the-art, open production-ready models, and we do it very openly, open data, open models, open weights, and we do train with the open source Nemo toolkit, where you can use it for training, fine-tuning, and running for the speech AI models. Our team mainly works on 3 model areas: ASR, text-to-speech, and speech LLM, which I'm going to talk about in the future slides. So now I'm going to talk about the Nemotron family of speech models and also various speaker models. The first one is the Parakeet, which is the fast and accurate ASR model. We have 2 variants of it, English and multilingual in 25 languages. The next class of models I would like to talk about is the Nemotron ASR models. It's the same class as Parakeet with the similar encoder with the cache-aware architecture. It's trained for real-time transcription and multilingual. We just released the Nemotron 3.5 ASR. It handles 40 languages and variable low latency as well. The next class of models is the Canary. It does 2 things: multilingual transcription and also translation with a greater accuracy across the 25 languages. Canary Quan also falls under the Canary class of models, but it has a LLM backend. We use Quan 2.5 as our first LLM backend for the Canary class of models, and we are working on the next versions of it. The final but not the last model is the streaming short form model. It's really fast, tiny model, and it handles multiple speakers for speaker diarization to know who spoke when. And all these models are open source. Every model is released by CC by 4, so you can download for free on Hugging Face and give it a try if you haven't already. During this talk, I would like to focus mainly on Parakeet class of models. These are the models we designed especially for handling the workloads of everyday use cases on edge devices, cloud devices, and also the desktop class devices. So we wanted to build it especially for this rich ecosystem. So, and we are very happy to see the users finding it really useful. So we saw greater traction for this. Approximately, we are seeing 1 million downloads per month on Hugging Face. As I said, it has rich ecosystem right now. If you like to try on Parakeet.cpp, MLX, OnX, MCP servers, desktop applications, whatnot. So if you haven't already, I highly suggest you to give this model a try. We did release on 2 versions, V2 and V3, English and multilingual variants as well, especially for the European languages. It was recently featured in the HF Richie mini robot as well, which does real-time speech-to-speech transcription, interactions especially, and Parakeet was also used for transcription. So that shows that the model is really capable of handling real-world use cases. Now, speaking of real-world use cases, it's really important because we want to talk about how these models handle actual noise, or maybe the far-field noise, which is really useful for all the agentic stuff these days, maybe robotics, or maybe when you want to use it in your everyday use cases. We do have OpenASR Leaderboard, which has become the standard for ASR evals, but it has few data sets like eval sets, which are like earnings and AMI, which covers the real world use cases, but it's not close in terms of how we measure for noisy, far field, and real world results. So it's really essential that we need a leaderboard which can handle or which can actually measure and benchmark different models to evaluate on this, especially for distance, to evaluate how these models are performing for a far field voice. This is going to be really useful for like drive-through scenarios, and robots for reverberation, etc. If they're living next to you in the room, background noises like HVAC, TV, traffic signals, for example, and all these are really important scenarios which we need to consider, but we kind of like the leaderboard for it. Speaking about the noise, it's really important to build these models for robustness. So for Parakeet, we handle the robustness in 2 fronts. One is architecture and the data. For architecture, we use the fast conformer encoder and the TDT decoder. TDT decoder is really useful for bringing the robustness to the model. We moved from RNNT for the V1 version to TDT because first of all, it's fast and also helps in the robustness, because along with the token predictions, it also predicts the duration, which helps for robustness for the model whenever there is noisy scenarios. And since we use this architecture, it always makes sure that the output tokens are always lesser than or equals to the input tokens, which is the acoustic tokens. So that way there is very less room for hallucinations in the first place. So along with architecture, one more really important factor that played a big role in robustness is the data. And for this, we use the Granary data, which is the open and reproducible pipeline that we built for generating these pseudo labels. Granary data was built on open data. It consists of 1 million hours of data, which is multilingual data, 650K hours of ASR data, which is multilingual, and also 350K hours of translation data. This translation data consists of EN to X pairs, so across these 25 European languages. With the architecture and the data, we train the Parakeet models, and it really shows up how the model performs under noise. As you can see in this bar charts, when we evaluated on the OpenASR leaderboard, the model really shows its performance even under noisy conditions. As you can see from the clean to SNR of 5, which is really no low signal to noise ratio, the model only struggles by 2.3 percentage points, which shows the model is doing really good. But for this, we used music and additive noises. I'm pretty sure it doesn't cover all the scenarios which we used in real world use cases. And this is where the FFASR leaderboard comes into the picture. And here we Hither Treble Technologies, along with partnership with Hugging Face, has built the leaderboard, which is really useful for benchmarking the models on real-world noises, where maybe the speaker is moving, or different use cases like reverberations and all the different types of noise levels. So over here, it's great to see the Parakeet models ranking 3rd and 4th on the leaderboard. And due to the decision we have taken in terms of designing the Parakeet, the accuracy along with the higher throughput also takes into consideration, and we can see that Parakeet models leads across these both fronts, considering the higher throughput along with the great accuracy. And this far-field leaderboard matters really because it helps us for giving the better rewardness for the robustness of the models, and it exposes failure modes like hallucinations and the performance of the models if they're really good on maybe near-field data or maybe like the clean data. These leaderboards actually expose us for the real-world use cases, and it's realistic. I mean, it considers like various noise and signal to noise ratios levels. So it's really, really useful for evaluating. And having this leaderboard also helps us to build the next generation ASR models that will be shaped for all the agentic use cases and different speech-to-speech interactions as well. So I hope this information that we have given on how we build the models is really useful even for you to start taking up these models and fine-tuning. And as I said in the beginning, our goal is to make all the models open. So open data, open models, open toolkit. With the latest version of the Nemo toolkit, we also integrated agentic skills. So if you have the data, you just tell the agent and it should get you started. And of course, more data and more models are coming soon. So stay tuned. Thank you.
Hi, yes, thanks for having me. My name is Julian Mack. I'm a member of technical staff here at Cohere. And today I'm going to talk about Cohere Transcribe, our ASR model that we released recently, and how that relates to the far-field context and how challenging that is really for the latest models. Okay, so for those of you who haven't heard about Cohere, we're the leading foundation model provider focused solely on enterprise. So we build models and products that solve real-world business problems. We have our flagship platform, North, and that can be deployed wherever the data is. So that might be in cloud, but it's more likely to be on-premise or in a customer's virtual environment. It can even be air-gapped. So Cohere does not see the data of their customers, which makes our solution perfect for a lot of regulated industries. And we partner closely with a whole load of global enterprises, and we're growing very fast. So it's a very exciting time for the company. So on to Cohere Transcribe. So this is our first audio model that we've released. We did it in March, so a few months back now. And essentially, it's a simple recipe that we've scaled up to make it robust in various settings. We're using 500,000 hours of really high quality data and a lot of background noise augmentation to really get that robustness. In terms of the model architecture, it's a 2 billion parameter model, an encoder-decoder model with cross-attention, and we're using a fast conformer, so thanks Nithin and Nvidia for that contribution. We have put about 90% of the parameters into the encoder, which gives us really, really fast inference, and it makes it cheap to serve. And the model is Apache 2. We had day 0 support in transformers and VLLM, but it's not just an open source model. So this is running today in North in production with our users. On the day that we launched, we were at #1 in the Open ASR Leaderboard, although things have changed since then, so congratulations to George and IBM for reclaiming the top spot with Granite 4.1. A few more benchmarks here on multilinguality. So this is really important to everything we do at Cohere. There are 14 languages that we support out of the box, and these are chosen to be the business critical ones for our customers, rather than language similarity. We're using the same 16K tokenizer for all 14 languages. And one thing about the setting in which Cohere builds models, because of the fact that we're likely to deploy these in a customer environment on their hardware, there is a really strong incentive for us to build as few models as possible. So we can't have a single per language speech recognition model. And we also probably can't have a near field and far field separate systems. We need it all to be in a cohesive foundation model, which makes it a really challenging and exciting problem to work on, to be balancing all of these tasks and capabilities in a single system. So why are we talking about this today? So why do our customers care about far field? Well, there are quite a few use cases in which this is important for us, but the key one is meeting transcription. So in many cases, meeting transcription could be near field. So it might be someone speaking to their laptop or with a headset. But in many other scenarios, you have a conference room with maybe only a single microphone or a device that has multiple mics, an array of mics. And in that context, we're going to need to still have really high quality transcription. Okay, and so what are the new challenges that are added in the far field context? Well, I don't want to dwell too much here, as lots of people have spoken to this, but maybe just to pull out one difficulty that is added in the ASR context, which is that when you have a conference room mic, or in fact, it's not a single mic, it's an array of mics, that's going to be performing on-device beamforming, probably echo cancellation, and it will be auto-mixing it to a single channel, or maybe a two-channel output for the ASR system. And so that is important because it means that your system now doesn't just need to be robust to the vocab of the speakers and the fact that we're now in a far-field acoustic setting, but it also is going to need to be robust to the different artifacts introduced by the different microphones and their on-device DSP pipelines. So this is an extra layer of variability that you have to be robust to when you're trying to create a single foundation model for all of these settings. And maybe just to pull out a timestamping complexity in far field, if you have a lot of reverberation in your conference room, that is going to smear this phonetic evidence over time, and it's just going to make it much harder for the model to get really crisp word boundaries. So onto the leaderboard. I think from what we've seen, this is a really strong contribution to the community. And the main reason is that it seems to be really hard. So there's a rule of thumb that says you need your speech recognition model to be below about 30% in order for the transcripts to be useful. So looking at the results, it seems like all of us model builders on this call have a lot of room to go, particularly in the low SNR setting, which is exciting. It's great to have benchmarks that show us where progress is needed. And another thing that we like about the leaderboard is that the far field word error rates are put alongside the clean speech ones, which means that we can use the leaderboard to see what sorts of things are going wrong. And the picture that is painted here is that it seems like most of the best models today do well on the clean audio in this benchmark, but they separate pretty sharply in far field conditions, which aligns with what we're seeing with near field benchmarks. There's quite a lot of near field benchmarks that are fairly saturated today, but clearly there's a load of work to do to achieve proper robustness in far field and in noisy environments. And that's particularly true when you're trying to do that in a single foundation model. So that's all from me. Thank you so much for the opportunity to talk today about some of the work we're doing at Cohere. We're hiring, so if any of this sounds interesting, please do get in touch. And yeah, thanks very much to Treble and to Hugging Face. I'll pass it over to the next speaker.
Hello everyone, I'm Shinji Watanabe. I'm now in the Carnegie Mellon University Language Technology Institute. So, and then I just want to discuss about my kind of introduction of our research activities and the thought about far-field speech processing. And before moving to the technical discussions, I just want to introduce my university and my department. We are in the Language Technology Institute, and this is actually department of working on the language technologies, including NLP, the human language speech communication, multimodal machine learning, and so on. And the entire department, we have 32 core faculty members, and we also have a PhD course and several master courses and so on. And I am belonging to this Language Technology Institute and working on speech processing and audio processing. And my lab is called CMU Web Lab, and launched 2021, I moved from Johns Hopkins and then created this laboratory. This is actually regarded as one of the largest speech and audio research laboratories. Our group usually kind of submitting a paper, accepting the paper is accepted the top venue in speech, the audio, NLP, and machine learning venues, approximately 60 or 70 papers per year. And we also have a lot of the activities additionally to the publications like our keynote talk, tutorial, and so on. And our group actually is also having a lot of achievement. This is just a kind of the example of the achievement. And actually, I'm very glad that recently in the ICASP, the 1 month before, we also got the Best Student Paper Award. And including this, we also have a lot of other awards. And this kind of great achievement is done by my other great students and colleagues. And these are our current laboratory members. And all members are actually working on speech and audio processing. And I just listing the several kind of research topics, like multi-speaker conversational analysis, multilingual processing, assessment for generative audio speech, spoken dialogue systems, and multimodal foundation models. And then our lab is also the working more in the focusing on the benchmarking. And this is actually one of our lab style. We are working on, for example, organizing the Chime Challenge. We also maintain a toolkit called ESPNet. We also are organizing several other the research activities like a SPURB, Urgent Challenge, and the Versa Toolkit, and so on. And let's discuss about some of recent the project in speech recognition, which is the open whisper style speech model. We call it OSAM. And this model, we try to make our kind of foundation model to be fully transparent. And including other kind of the research, the institution that building a speech recognition system, our models is the first, it is kind of fully transparent. Second, we also using the all kind of public data so that our kind of models are fully reproducible. So this can be probably very unique compared with the other research institutions. They're usually using their own data to train the models and so on. And recently, our kind of this kind of activities are getting some good milestone. This one, as the name shows, we actually try to reproduce OpenAI Whisper model. And last year, we finally got the comparable or slightly better the speech recognition performance in the OpenAI ASR Leaderboard organized by Hugging Face. Compared with the Whisper large model and so on. Nowadays, a lot of kind of better system exists, and this is a 2025 result. I'm very proud of this work because compared with all other models, this work is fully transparent, as I mentioned before. Okay, so now we move more about the far-field speech processing, and this is very related to the new leaderboard. Our group has been working on the far-field speech recognition for a long time. And as you may know, classical speech recognition was developed in the kind of a crosstalk microphone and single speaker scenario, which is kind of good for the people to asking the command to the computer. But what is our actual conversation? Our actual conversation, there are a lot of people, and the microphone may not be kind of close to ours, and then we need to actually communicate. We need to understand what people are communicating each other. And let's talk about what is far-field speech recognition and how this kind of is difficult. This comes from the lot of factors, but mainly considering from the 3 factors. One is background noise. The other is the interference speaker, and the other is reverberation. So these are very kind of difficult problems. And then I'm very glad that the Far-Field, the speech recognition leaderboard is tackling this problem and so on. And actually this the approach, the Far-Field speech recognition, we have been working in for the very long time. And one of the activities in our group is to organizing the Far-Field speech recognition called Chime Speech Recognition and Separation Challenges. And this one is actually we released in 2015, so it is already 10 years ago. But we actually are handling many of the difficult speech recognition problem like this.
A year earlier, CMU had first quarter profit of $116.2 million, or 77 cents a share.
These are cafe scenario.
Base rates are the benchmark for commercial lending crypto.
This is a street scenario.
Rates are expected to remain at those levels or move a little higher this week at the Treasury Department's quarterly auction.
This is a bus scenario.
Sources say at least 2 bidders had some doubts about Citicorp's performance numbers.
This is a pedestrian the area scenario. And these are kind of very challenging the speech recognition problem. And at that time, we again organized a kind of a challenge, and we have a leaderboard, something similar to the Far-Field, the ASR leaderboard. And these are kind of a result at that time. And I'm very kind of excited to have our more advanced the technologies and the leaderboard in this kind of new the Far-Field ASR. And then moving to the more kind of the realistic conversation, we actually focus our target to the multi-speaker problem. This is the Chime Challenge 2020, and then since then, Chime Challenge is actually more working on the multi-speaker scenario. I can just play with some of the audio.
So what do we do, Dad? How was your day?
If you have ideas about what to do.
So,
This is one of the kitchen scenario.
This is all the effort you did to eat the lobster. Like, at least eat the crab top.
This is one of the dining scenario. This is one of the living room scenario. And honestly, I even cannot well recognize what people are talking in this recording. And the initial word error rate of this kind of baseline in 2020 was actually the 80%. 80% is not accuracy, 80% is the error rate based on their kind of the state-of-the-art technologies at that time. But we have a lot of additions in this kind of challenge, and nowadays one of the state-of-the-art techniques is reaching to the around 30%. By the way, I also want to emphasize that with this kind of multi-speaker scenario, it is very difficult to also compute a word error rate because we also consider about multi-speakers are speaking and also they are also overlapped. So we are also creating a lot of metrics to how to kind of evaluating this kind of conversational the speech analysis and so on. Okay, so this is actually my kind of the talk in general. So nowadays the people are moving toward the conversational the speech analysis, And this is not purely speech recognition or not purely speech enhancement. We actually have to include all kinds of speech aspects, like a speaker characteristic, timestamps, like a speaker diarization, emotion, speaking style also affecting the conversational speech understanding, intention, recording condition, acoustic spatial environment, all should be considered if we understand the conversational scenario. And this is possibly one of the very exciting research area in our field, which is try to kind of making a model to combine all the speech technology to tackle speech analysis. So I'm very looking forward this Far-Field ASR benchmark to also deal with this kind of exciting conversational understanding scenario. So that's it. Thank you.
Thank you so much to all the guest speakers and Hugging Face. It's been amazing insights to the collaboration, what you guys are working on and so on. And we really hope that this leaderboard is something that will be picked up by the community and help drive innovation and development efforts forward. So I wanted to take a quick dive with you into the leaderboard and how it is on the web page as it stands currently. Of course, models will be added continuously either by you or by us and so on, but at least here it is how it is today. So we see the leaderboard here with the different models. As mentioned previously, the average word error rate is what determines the ranking on the leaderboard. Next to it, we have the near field audio field. That could also be called dry speech, clean speech, anechoic speech and so on, but it's speech recorded in an anechoic chamber with a microphone in very close proximity by different people, males and female, speaking English with different accents. Then we have the high, mid and low SNR, which is this dry speech or near field speech convolved with room impulse responses from these 5 different environments, as well as various noise sources. Then we also have in the leaderboard, you could say, tabs that addresses the sim to real gap. So we have done measurements in laboratories, which we have also simulated with the exact same source receiver configuration. And here these ASR models are then evaluated on those, and we see that the scores are more or less similar for these two. Furthermore, it's also possible to evaluate how a moving source affects an ASR model. So you can toggle these tabs here, and then you see the different scores for the moving sources, essentially. Interestingly, also the average word error rate on the left here is computed from whatever boxes are ticked. So, for example, if I deselect the near field speech, we see that the average word error rate is updated. So you can customize a leaderboard basically to your liking. If you want to submit a model, you do that through the Submit tab. You can put in for example, a public model ID here. So I'll just put in a model here that we have as an example, this Cohere model, like this. Then you can, when you specify, it would be very helpful if you can specify if there are certain Python requirements or libraries that you need for the evaluation. Of course, we have all the standard ones like NumPy and so on. But for example, if you need a custom one like sentence piece, you can write that in here and we can use that. Similarly, if there's custom shell scripts or other things that we need to run, you can put this in this field. And then finally, it would be very helpful for us if you can provide an evaluation script for your model, so we have a very good starting point when adding it to the leaderboard through our moderation panel. If it's a gated repo, you can check this box.
Just keeping things calm in the background.
Thank you, Richie. That's very helpful to know. And if you have optional notes for us, the moderators, you can type it in here. And similarly, if you want to be contacted by us, for example, you can write in here, I would like to see the eval script. You can type that in and then type your email, and then we can send that to you before we put it on the leaderboard. And then you basically click this evaluate button, and then it's submitted. We also have an analysis tab here where we show different kinds of plots visually. One would be the Pareto plot, which I personally like a lot, that shows this trade-off between the average word error rate, but also the real-time factor. So if you are either competing on the leaderboard or you are looking for a model to use for a certain application, here you can really visualize, you can say, the trade-off between accuracy and speed between these different models. Of course, we also have visualized scores on word error rate if you're competing on that, speed if you're competing purely on that. We have a heat map across all the different eval conditions in the dataset, as well as a bar plot for for the top 8 models essentially. And we're constantly looking for feedback here. So if there's a plot or some visualization that you would like to see, don't be shy and reach out to us, and we'll add it in. Then we have an examples tab where you can see an example of how a model would look like, and you can also play these different speeches, like near-field speech, the different SNR conditions and so on. And I'll go into a little bit greater detail with that in a second. Regarding the sim to real gap, we at Treble had done some investigations where we have physical spaces that we have measured, and then we have corresponding simulations virtually with the exact same source receiver pairs. Here we have evaluated different downstream tasks, both on measured data and simulated data, and we can see when we use high quality simulations such as the wave-based approach, a final element method that solves the wave equation, you get similar results between measurements and simulations, as shown here on the left plot. If we use more approximate methods, as shown on the right, we see that you can say the correlation or the trend is not really captured by the simulations, and that is why we can use these high accuracy simulations for this leaderboard, because it's a scalable way to generate high quality acoustic data, which we can then also expand on across different environments, movement, etc. If you're curious about the underlying simulation technology or this comparative study, we have a paper in IEEE that I encourage you very much to check out. So I wanted to take a short deep dive on the data behind the leaderboard to give you a bit of a fingertip feel for what this looks like and how we made it essentially. So as I mentioned, we recorded some dry signals in an anechoic chamber here in Iceland, or anechoic speech, that will then convolve with room impulse responses and noise sources that is also convolved with room impulse responses. So just to give you a feel for how this sounds.
I paid $873 for the chair plus $64 for shipping.
The sound will then convolve with a room impulse response. So I'm going to go through 3 different cases basically. So here's the high SNR case. Note that we have the target speaker here in the kitchen and the receiver being quite close in proximity. And then we have 2 noise sources in this hallway essentially. So let's see how this sounds.
I paid $873 for the chair plus $64 for shipping.
So it's very easy for us to make out what the person is saying, but we also hear that there's some background noise, of course. So moving to the mid SNR case, so here the noise is of course a little bit louder, but one thing that also you can say determines the signal to noise ratio between target speech and the noise sources is the distance between the target speaker and the receiver. And here we know that now this distance is greater in this case, as well as the noise sources have been amplified and also are different.
I paid $873 for the chair plus $64 for shipping.
So we have, again, the 2 noise sources here in the hallway. I forgot to mention that we also have some device noise here, some pink noise that's also added to the signal. In the low SNR case, here you can say that the speaker will become a little bit more inaudible because the noise sources again are louder, but also the receiver has moved even further away and now sort of close to the corner out here, while the target speaker is still in the kitchen.
Paid $873 for the chair plus $64 shipping.
So definitely a difficult case for the ASR algorithms. And then finally, I wanted to just show you a quick animation of how a moving source looks in the simulation tool for these different use cases. So this one will be without sound, but we see that it moves, for example, in this case, from the hallway and then into the room, and that could be one example of how this is made in this eval dataset. I will now switch over to showing you here towards the end, just giving you a bit of a feel for how the data is structured. What are the, you can say, different T20s, source receiver distances, and so on. So you get an idea of how the data essentially looks behind the scenes. So here we can visualize T20 for all the different source receiver pairs. Perhaps it's easier to see in sort of a violin plot. So it is a little bit jagged. We have these kind of 14 different rooms of varying sizes. So and that's sort of then we get this T20 profile essentially. We could also look at C50, the clarity index. We have that here. Distribution from more or less -5 to 20. And then perhaps at least interestingly for the different SNR cases, we have the source receiver distance. So this is what we see here. So we see that we have distances ranging from about a meter all the way up to 10, maybe a few cases with even 14 meters, but I would say like 1 to 8 meters is the typical case. We also see that the source receiver pairs have a broken line of sight. So in this case, we have, you can say the green color here is the source receiver pairs where they can see each other. And then the blue here, we see a nice distribution of source receiver pairs where you can say the source or the receiver, for example, is behind a corner in a hallway and stuff like that. Which also, you can say, adds difficulty to the problem. Thank you everyone for tuning into this webinar. We really appreciate that, and we look so much forward to put this leaderboard out to the community, and we're sure that will foster innovation and competition going forward. Thank you so much to Eric from Hugging Face for helping with the leaderboard and creating it and giving valuable feedback. Thank you so much to our guest speakers, George from IBM, Nithin from Nvidia, Julian from Cohere, and Shinji from CMU. We really appreciate you coming here, presenting your work, taking the time out of your busy days, and also hosting us while we are traveling around the world visiting you guys. And yeah, we're ready for a Q&A in a minute. Put your questions down below, and we'll answer them live here. And Richie, maybe you would like to say goodbye to the audience as well.
Thanks for having me. Signing off. And remember, a robot never forgets unless I crash. Bye.
Bye.